Good morning to all the learners in the Free State. I hope I have a large audience. If not, you can always look at the video afterwards. It will be available on YouTube. Now, if there are teachers, ladies and gentlemen, the purpose of this broadcast is to discuss the control test memoranda or marking guidelines, if you like to call it that, of the control test that we wrote in March. For the learners, I have a short message. Point number one is I hope this will help you. I'm going to try my utmost best to help you to understand what mistakes you have made, etc. Because there was a big uproar about the marks based on the information we got in physical sciences as well as in technical sciences. The reason for that is that both these papers were primarily set to identify shortcomings that learners might have. And the examiners have focused on identifying questions that can address the mistakes highlighted in the diagnostic report. Now, all teachers have listened to the conversation by the subject advisors during the startup meetings, and the idea was that learners don't repeat those mistakes. So to the learners, I want to say, it's better that you make those mistakes in March than in November. And if you didn't do so well in the test, don't focus on the low marks that you got. Focus on identifying ways and means and better understanding that you can improve and that you don't make those mistakes again in either the June examination or the September examination or the November examination. Because the March mark contributes less to the SBA mark than the rest of the marks that are coming this year. And it is really important that we focus on improving these things, because fact of the matter is, if you cannot do well in the March test, you cannot do well in any further examination. You have to solve these problems more successfully. And by discussing this thing, I hope that learners will benefit by that and that it will also save teachers a little bit of time. To the teachers, I want to say, if you see I miss something, you are welcome then to just add. But by discussing this memorandum, the way we do via IBP, it might help you to you know, that you don't spend that much time in the class to do that, because time is limited. Now, various topics in the test for physical sciences and technical sciences overlap. So what I'm trying to do now is to discuss both these tests. And I'm going to start with the technical sciences. And if I don't forget, I will indicate every time whether a specific question is applicable to physical sciences as well. So when I discuss technical sciences, the physical science learners can look as well. When I discuss technical sciences, when I discuss physical sciences, the technical science learners can look as well. So don't switch off. Come with me and let's see if we can help you to sort out these mistakes, because it doesn't help to complain about low marks and not improve your errors. And that is the big thing that we want to do this morning. Complaining about the marks is not going to solve better mark hunting or hunting for better marks. It is about you solve the problems and you sort out incorrect ways of thinking, etc. So let's dive right in, and I am going to talk about the multiple choice questions of technical sciences. Now, the first one is also applicable on physical sciences. So remember, the first one is applicable on physical sciences. And I'm reading for you: the inertia of a body can be defined as the rate of change of its velocity, a force acting in a string or a rope, a force acting parallel to the surface and opposes motion, and the property of a body to resist any change in its state of motion or rest. On this question, I want to say, the important thing is you must know your definitions. Learners, level 1 questions are dealing with definitions. And if you don't know your definitions, you cannot get those marks. And the definition is asked either like this one in a multiple choice question, or it is asked to be written down. And either way, you have to know your definitions. It's actually easier to answer a definition via an MCQ than to write it down. And the important thing is you have to know your definitions. The main reason why learners don't do well in question papers, I might sound as if I don't care about you. The point is, you don't do well enough in your questions because you can't handle the easy questions successfully enough. People don't fail because of the hard questions in the paper. They fail because they don't manage the easy questions well enough. Now here is one. They want to know what is the inertia of a body. So obviously you have to go through them. The rate of change of its velocity. One can write down a formula for this. The rate of change in velocity. Now if we talk about the rate, it's always divided by time. The rate of change in its velocity, there's change in its velocity, divided by time is rate, and they want to know is inertia this. Now this is meaningless. Né? We have a formula or a definition that says the rate of change in momentum. Now that is equal to the net force. A force acting in a string or a rope, etc., etc. And when you come to number D, it is the property of a body to resist any change in its state of motion. So there's your answer for question number 1.1. 1.2 is also applicable to physical sciences. Forces in nature always exist in pairs. A nail is hammered into a block of wood with a hammer. The reaction force the hammer experiences. Now what I want to demonstrate here is you must always be prepared to draw a diagram for yourself or to highlight keywords, etc., etc. Now, some time ago, we have done a video on Newton's laws of motion. If you go through the IBP channel of Free State, I just want to say Bobby is our technical man today. Bobby, thanks for the effort you put in to help our grade 12 learners. We really appreciate it from the department side. Bobby, the channel for YouTube is called FS-IBP. And that is your channel where you can find all your videos. And some time ago, we have done a video on Newton's laws of motion. And in there, I have discussed a few things. But to help you, I think let us check this scenario because many people don't get this thing right. They talk about a hammer. Now, I'm just going to draw a little block, a hammer, a nail, and a block. Let's say we have these three. So the H, the N, and the B represent the hammer, the nail, and the block. Now imagine you hit the nail with a hammer. So you bring down the hammer and you hit the nail. So the nail experiences, and I'm going to write it like this. This is now the force of the hammer on the nail. Okay, so H on N. But due to Newton's third law of motion, there is an immediate and simultaneous force on the other object. So if the hammer exerts a force on the nail, then the nail exerts a force on the hammer. The nail on the hammer. And this force is equal in magnitude and opposite in direction, and it happens simultaneously. So these two represent one action-reaction force pair. And look at the labels. When I deal with Newton's third law of motion, my tip is always write down descriptive forces. In other words, the force of the nail on the hammer. In other words, by what, on what. The force by what, on what. In Afrikaans we say die krag deur die spyker op die hamer. In other words, the hammer on the nail. By what, on what. Now, because of that, obviously, the nail will exert a force on the block. So on the block there is a force of the nail on the block, and simultaneously with that there will be a force of the block on the nail. And these two are one set of action-reaction force pairs. Now you can go on like this. The earth is here, there's obviously a weight, the weight of this thing, etc., etc. I don't want to make it too complicated, but if you look at the question asks the reaction force the hammer experiences. So we want to know what is the force on the hammer. Now, there are always little ways of getting out of a multiple choice question. In other words, sometimes you can answer a multiple choice question correctly without knowing the physics or the chemistry. And in this case, if they ask you the force on the hammer, there is one possibility: on the hammer, on the nail, on the hammer, on the block. So it can be either B or D, because that is the structure of a multiple choice question. So now you need to identify what is going on. Now, I don't want to motivate you to answer multiple choice questions by guessing or by playing games. Rather, understand the physics. The reaction force the hammer experiences is, now what happens here? The hammer hits the nail. So the force of the hammer on the nail, the reaction force to that, this is the force they talk about. This is the force the hammer exerts on the nail. In other words, the reaction force to this one is actually the force of the nail on the hammer. And if you look there, the nail on the hammer or the block on the hammer. So your answer is B. And a very powerful technique that you can apply is always this thing of labeling your forces like that. Only when you deal with Newton's third law of motion. In other words, when you deal with calculations and so on, we will use more shorter symbols. But in the case of Newton's third law of motion, you will become very successful if you apply this method. So the hammer on the nail on the hammer. If these labels swap places, then it is normally an indication that it is a reaction force pair. In other words, the hand on the wall on the hand, the ball on the earth on the ball. You know, that type of rhythm is very helpful if you want to deal successfully with Newton's third law of motion. Question 1.3 is also fine for physical sciences, so it's important that the physical science learners follow this one as well. A block is resting. Now, the word resting is always important. A block is resting. It means it is stationary. In Afrikaans sê ons, dit staan stil of dit is in rus. In other words, it is resting on a table. Now, to rest, you have to have forces that give you a total force that doesn't cause the block or whatever to go around, to move around. But we don't use the term total force, we use the term net force. So if it is resting, the net force should be 0. Then they say force F is applied to the block as shown in the diagram. Now you can see the force F is applied at an angle theta to the horizontal, and the object remains at rest. In other words, what happens here is, and that is a very important thing to realize, the block was sitting on the table, stationary, resting on the table. And now the force F is applied. So the block was already stationary by the time the force is applied. Despite that, the object remains at rest. In other words, doesn't move. Which one of the following will not influence the magnitude of the frictional force on block M? Now, this is important. This question is asked in a negative way. In other words, you have to identify the correct ones, and the one that is not correct is actually your answer. There's not many of this type of questions, but they are normally there. Okay, so which one of the following will not influence the magnitude of the frictional force? We must probably now decide what is the frictional force. Now, according to our formula, and you do remember that at the end of the paper, you always have a set of formulae. So use them as they are here. Very helpful. Don't make mistakes with formulae. And there are the frictional force equations. In other words, the ones if the object is stationary, as well as situations where it is moving. So I'm not going to write it down very complicated, but it is actually equal to the constant, mu, multiplied by the normal force. Now in this case, we must probably check what type of forces do we have here. So let's draw in the forces that we have. Now first of all, and remember, when I draw the forces on this diagram, we call it a force diagram. When you draw it as a little dot with all the forces on it, we call it a free body diagram, and then we only look at one specific object. Okay, so let's think about the following. Let's see. The block has a specific mass. Due to that, this block will have a weight. So I'm going to put a small W. I was thinking to say, remember in physics, we use a capital W for work. In other words, in Afrikaans, arbeid is a hoofletter V, but weight, in Afrikaans gewig, it's a small W. Okay, that's the weight. Now, because of the weight, this body is pulled onto the table. Therefore, the table exerts a force on the body, and that force is called the normal force. Now, I'm just going to put it in here, a normal force. Let's say that's your normal force. What else? We have this force from the left-hand side. Now, this force, let me color it. Let me color it in green. Now, because it is acting at an angle to the horizontal, it is important to realize now that this force has a vertical component like that and a horizontal component like that. Let us call this one V vertical, and let's call this one F horizontal. Not V vertical, F vertical. My apologies. F vertical, F horizontal. Please remember, when you draw free body diagrams, in other words, the one with a dot, do not include components, because I want to talk a little bit about these two things. Somewhere in grade 11 and grade 10, you have learned about addition of vectors, and that is something very important to realize. Let's say Peter is walking from this point to that point. Let's say he walks in a straight line for 5 kilometers. Then we say his displacement is 5 kilometers. And let's say we have a scenario where it is north, east, west, and south. So we can describe this as 5 kilometers due east. Let's say he walks another 2 kilometers due east. Now, if you construct this, it means if you use 1 centimeter for 1 kilometer, this line will be 5 centimeter and then 2 centimeter. If I now ask you, what is the resultant displacement of this boy? Then the technique that you apply is you take the tail of the first vector that you have drawn in the tail to head method, and you take the last vector, and you link these 2 points with a line, with an arrow, and the first vector's tail and the last vector that you have drawn's head. The vector between these two is the resultant displacement. Now let's say we measure it and construct it, etc., etc. We will get 7 kilometers due east. Ne? The very same thing if I have a distance of 10 kilometers to the east and let's say 1 kilometer to the west. What is my resultant displacement? Once again, you take the tail of the first vector and the head of the last vector, and you connect the two, and you make sure that the head of this vector touches the touches the head of the last vector and the tail of the first vector. Now this one will obviously be 9 kilometers pointing to the east. This is the resultant vector. So in other words, what we have here is addition of vectors. 5 plus 2, both in the same direction, give you a resultant that is greater than any of them, and one east and the other one west give you a resultant displacement which is larger than the one and smaller than the other one. We can do the very same with forces. Let's say I have a force of 5 Newton and 2 Newton, then I will have a resultant force of 7 Newton. And if I do it with a calculation, then I can do the following. I can say the resultant force, and we like to type that in terms of forces as net. The net force, if this one is F1 and that one is F2, I can write F1 plus F2. And if I take to the east as positive, then this one will be a positive 5 plus then, and this one, this thing is an operator. And F2 is then plus 2 Newton. You can put plus 2 Newton if you like to, doesn't matter. And that gives you plus 7 Newton. Now the fact that it is a plus, it means it is towards the east. If I do the same here, let's say F1 is equal to 10 kilometers, sorry, 10, we change this now to Newton, Newton, and Newton, and we still take positive to the east, then this one will be F net is equal to F1 plus F2. And now you must look carefully. What is F1? F1 has a magnitude of 10 Newton, and it is towards the east. So if I take towards the east as positive, then it means it's a positive 10. That thing is an operator. This plus is a sign to indicate direction. So here is my operator. Then F2. F2 is 1 Newton west. So the magnitude is 1, the direction is west, therefore it must have a negative. Therefore you get plus 10 minus 1, and that gives you plus 9 Newton. Now this part is the magnitude and the unit, and this part tells you something about the direction. So it means the net force or the resultant force is then 9 Newton due east, towards the east. Now in very much the same way, we have this scenario where you don't have the components, and let me come back now. This one and this one are called components of this one. In other words, the result of these guys, the net force, is the result of those, but those are called the components of this one. And very much the same way, this one and that one are called the components of F, because when you have two-dimensional vectors, in other words, vectors that work in 2 dimensions, vertical and horizontal, for example, then you can apply Pythagoras' theorem to get these values. In other words, the square of this one plus the square of that one gives you the square of that one, and therefore you can use it to calculate the magnitude of F. And you can also use the trigonometry functions sin, cos, and tan to determine the angles, etc., etc. So what is very important is you must learn and remember that because the force is applied at an angle, then it has a vertical component which is downwards. In other words, this one works with this one. The vertical component of F and the weight pulls this body onto the table. Therefore, the table pushes back onto the body, and that's the normal force. If this was not here, and this is the important part, if this was not here, then this one is equal to that one. But the fact that there's another vertical force downwards, part of F acts downwards, then it means you have a greater total force downwards. Therefore, the normal force must increase upwards. Right. And furthermore, the horizontal component of F obviously tries to push this body forward. So if it remains at rest, then it means there must be a force on this one to the left, and this force is most probably friction. In other words, the force of friction stops this body from moving. If I now draw these things as a free body diagram, I'm going to try to give you a good indication of what we have. Let's say FH is this size, in other words FH, then it means the frictional force must have the same magnitude, okay, because it doesn't move. And if this is the weight, and you have a vertical component, of, a vertical component of force F, then it means the normal force must be equal to these two together. So the normal force, we can draw it slightly longer. You can put it as Fn, or you can just put it as N. We have agreed that N is a good symbol for the normal force. So I take a bit of time to discuss this, but this is the type of thing that goes on in your mind when you deal with these things. It is really, really important that you deal with this way. And this gives us an opportunity to understand the physics much better. Now, let's see. Which one of the following will not influence the magnitude of the frictional force? Let's take them one by one. The angle theta between force F and the horizontal is decreased. So what you do is, you do this. Now you can imagine, and you can go and practice that either graphically or by using your mathematics, your sin, cos, and tan. If your angle decreases, then this little component will decrease as well. In other words, this one will decrease. So the total downwards decrease. Therefore, the upward force, the normal force, also decreases. And the normal force is part of the equation for friction. So if N changes, F changes. So if you change N, F will change. They ask which one will not change it. So this is not our answer. The contact area of the block is increased. Now that's interesting. Nowhere in this equation is area present. And that is actually your answer. And that is a funny thing that many people in ordinary life do not know. And that is that the contact area of anything touching any other thing does not influence the frictional forces experienced by the two bodies. The magnitude of force F is decreased. In other words, if you push slightly less hard, in other words, you don't push as hard, now F decreases, therefore vertical decreases and horizontal decreases. If this one decreases, the total downward decreases, so the N decreases again. Because remember, in all cases, the normal force and the vertical and the weight must be equal in magnitude. The sum of this and that one must be equal in magnitude. So the moment you change the magnitude of F, then the normal force will change and therefore the frictional force will change. The mass of M is increased. That means the weight will increase. Once again, a change here will cause a change there, and that one will cause a change in the frictional force. So your answer is B. It takes time to discuss these things, but I hope it helps you. And the point is, you must be able to argue through these things, because the next question might test the same principle, but using a different setup. And therefore, it is important to understand it. Here's another one, question 1.4, which is also applicable on physical sciences. A trolley is pushed along a horizontal surface by an applied force of 100 Newton at an angle of 45 degrees to the horizontal. The trolley experiences a frictional force of 45 Newton. Let us draw the forces again. And I'm just going to draw this one. That is our, let's just call it F. Let's just call it F. You can also call it the applied force if you like to. And because it is at an angle, there's a vertical force once again, and there is a horizontal force on this trolley. In other words, FV and FH are called the components. Then we also have the weight of the object, obviously. So there's a weight. Once again, this one and that one together pushes it down. So the surface pushes up onto the trolley, and that will be our normal force. So the normal force will be slightly larger than the weight, because the vertical and the weight together give us the same total as the normal force. And then we have a frictional force as well. So let's put in the frictional force here, and that is your frictional force of 45 Newton. Okay, so let's see what they have here. Those are the, I hope all the forces have been indicated. So it's weight, the vertical, because of the force, then there's a horizontal force forward, and there's a frictional force backwards because you push in that direction, and friction always opposes the motion, and the normal force. Okay, let's see. The net force acting on the trolley causes the trolley to accelerate horizontally. Now, can you at this point in time say anything about the acceleration of the trolley? You can't really, before you don't know how does this horizontal component of force F compare with this one. Because this one causes the trolley to move forward horizontally, and that component pushes it down on the ground a little bit more. And this is the 45 Newton frictional force. All right, so a trolley is pushed along a horizontal surface. Nowhere it says that it is at rest, so we must be careful here. Right, let's see what is the magnitude of FH. Now, FH is the adjacent side of this right angle triangle, so it will be the cosine of 45 degrees, and that will be equal to FH divided by the hypotenuse, in other words 100. And that will give you, I hope you can see this, so it's cosine of 45 multiplied by 100. I hope you can see that, so it's 70,7. Let us just take it as 71 for the sake of this exercise. So this one has a magnitude of 71. And what you see now is the horizontal force to the right is greater than the frictional force to the left. In other words, this trolley will go forward, causes the trolley to accelerate. Let's look at this word here. Why does it accelerate? Because with 71 forward and 45 backwards, the net force of the two, and that fits in now with this picture here. There is a net force in the horizontal direction of greater than 0, and therefore it causes the trolley to accelerate horizontally. So this seems to be fine. The net force acting on the trolley. Now, by the way, there are a lot of forces here. No? This one is actually applied via its components. So let's call this force 1, force 2, 3, and 4. Now, the net force on the trolley is 0. It means it is, if the net force is 0, it means it is 0 in all dimensions. Now, in this case, in the horizontal dimension, the net force is not 0, and that is why this thing is moving forward, but the type of motion it undergoes is the fact that it goes faster and faster and faster. While in the vertical plane, the normal force is equal to the sum of the weight and the vertical component. So in the vertical plane, the net force is 0, and that is why the trolley doesn't go into the surface or upwards in the air. That is why it stays on the surface. Right, number 2, the net force acting on the trolley is equal to the applied force. The net force acting on the trolley is equal to the applied force. Now, we have just said in the vertical plane the net force is 0, but in the horizontal plane it is not 0. So the overall net force is not 0. What is it? Well, it is the difference between 45 and 71. It is about 26. And so the net force is about 26. It's equal to the applied force, and the applied force is 100. So this sentence is not true. It is not equal. Number 3, the net force is horizontally forward. Now that we have said already, so this one is correct. So which ones will give us our answer? It will be 1 and 3, so the answer will be C. 1 and 3. Okay, can you see how many little bits of arguments you must come up with to do these calculations? It is important that you have a good knowledge of components of Newton's second law of motion, Newton's third law of motion, Newton's first law of motion. And you must know sin, cos, and tan, and you must be able to identify forces in different conditions. So that is actually the challenge to get good marks. But with experience, there's no reason why you cannot do that. 1.5 is also fine for the physical science learners. Now this one is maybe a little bit harder because it includes a graph. And the important part is, learners, you must learn to understand what graphs tell us. And always look at what type of graph it is. Without looking at the question, you can actually see this graph is it's a graph of momentum versus time. In other words, something is moving, and therefore the momentum was plotted against time. Now on the vertical axis it says momentum, so these numbers represent momentum, not speed, not change in momentum, nothing. It represents momentum. At each specific instance of the motion it represents momentum. And then time for a very brief period from 20 seconds to 20.3 seconds, so it actually represents only 0.3 seconds of the motion of this object. Now in your momentum problems, you normally deal with situations where bodies collide or where there are explosions. Now in physics, both of these are considered to be collisions. In other words, if two bodies collide, it is easy to understand that it is a collision. But what about something that explodes? For example, two cars, and you have a spring between them. So when you have two cars and you have a spring between them that is compressed. Now the moment when you release the spring and it pushes open, then during the time when the spring is in contact with this car on that side and that car on that side, it pushes the cars away. So although we call it a type of an explosion, we still see that as collisions in physics. And when there are no other forces acting on these objects, in other words, it's only the objects interacting themselves, then we call it an isolated system, and then the laws of conservation of momentum are valid. Right, so the graph below shows how the momentum of car A changes with time just before and just after a head-on collision. In Afrikaans, 'n kop-aan-kop botsing. In other words, the two cars come from opposite sides. So you can now come up with a little sketch if you like to. Let's say this is car A. And what do we see here? The car has a momentum of 30,000. There is 0, so this is a positive momentum. Now let's take positive in this direction. Then it means the car is moving in this direction. And let's say B is that one. Because it's a head-on collision, a kop-aan-kop botsing, then it means car B must go in that direction. So that is the situation before the collision. So this is before, voor die botsing, before the collision. After the collision, what do we see? The graph represents car A, and so the collision started there and ended there. In other words, the two cars must have approached each other and then either stay connected or moved in this direction and that direction, or do this and then go that way, or do this and then do that. You know, there are different combinations of what can happen. So after the collision, we see the momentum of the car A is 14,000, still positive, so it's still moving in the positive direction. It still goes that way. We don't really know what happens with car B after the collision, but as I try to indicate, there's no alternative for car B to either stick to car A or to move in the opposite direction. So in other words, if they don't stick together, then at least car B must also move in that direction, because it's impossible to move to the left if car A moves to the right. Now this is basically based on theory. Now during this collision, what happens? There is a very important piece of info here. Assume that the system is isolated. When that is the case, the laws of conservation of the principle of conservation of momentum is valid. Therefore, momentum is conserved and momentum is conserved. So it must be either A or D. And now the fact that that the velocities decrease. This guy's velocity decreases. Therefore, you can assume that kinetic energy is not conserved. In other words, there's a loss of energy during the collision, either by sound or whatever, and therefore these two are correct. Therefore, your correct answer must be number A. You can go into the mathematics for this and work it out, although you don't know all the numbers. It is possible to do that, but you are fairly safe to assume this, because with a collision you normally have sound and so on. And if you have numbers, you can actually calculate what is the correct values. Okay, 1.6 is also fine for physical sciences. Bobby, I hope we can finish this first part of the paper in the first hour. Okay, which one of the following is equivalent to the SI unit, is the equivalent of the SI unit of impulse? Now, to answer this type of question, the first thing that you need to do is you must think about the unit of impulse. And what is impulse? Think about your formula. If you can't remember them, here it is. F net delta T is equal to m delta V. Or if you don't like that way of writing it, you can say it is the same as delta P. In other words, change in momentum. Or if you don't like that, you can say m, the final velocity, minus the initial velocity. All three these are the same, and they deal with change in momentum. And change in momentum is equal to this one here, and this one is called impulse. So the unit of impulse, the SI unit of impulse for force is Newton, for change in time is seconds, and careful, it is not ns minus 1, it is just ns. It's actually a plus 1 there, but we never write it. So it is Newton times seconds. They want to know which one of these is the equivalent, in other words, more or less the same, or the same as this one. Now, it's most probably the best to say, well, what is momentum? What is impulse? Impulse is equal to change in momentum. And what are the units for change in momentum? Well, m is a kilogram. And change in velocity is meters per second. In other words, final velocity minus initial velocity, that represents change in velocity. And change in velocity is represented by delta V. And if you multiply that with m, you get change in momentum. So kilogram multiplied with meter multiplied by seconds to the power minus 1, or you can say kilogram meter per second. That one must be the same as this one, so there's your answer. This is a straight away level 1 question. So anybody who has this incorrect has a problem passing physical sciences, and there's no excuse. You have to go and study your work better. You can also do this by elimination. I mean, impulse, you know what impulse is. Kilogram is the SI unit for mass. Newton per second, there's the catch, né? There's the catch. It looks almost like this one, so the catch could be that one. And kilogram meters per second squared is actually the same as F net is equal to m times a. This one is actually the same unit as this one. Mass is represented by kilogram. Acceleration is represented by meters per second squared. So the combined unit for this part must be the unit for this one, and that is then Newton. So a Newton is equivalent to kilogram meters per second squared. Okay, but 1.6, our answer is C, and I hope I've explained it well enough. Where I skip certain things, your teacher can always help you, but your teacher will not know if you don't ask them. And you have to do the work. Né? There's this principle, BOC. What does it stand for? Bum on chair. Bum on chair for many hours and many hours and many hours. Revise your work, go through it, do it again and again and again, and don't complain too much about low marks at this stage. We want you to do good, but the low marks at this stage showed that you are not prepared for the rest of the year. So that's why it's important that you fix this up. Right, 1.7, physical science will do this very soon. In the second term, you are going to do vertical motion. So the physical science, not vertical motion, work, power and energy. So physical science learners will do this very soon. So you can come back later to this question, but at this point it might look a bit unfamiliar to you. A ball is thrown vertically upwards and returns back to the ground. Work done, technical science learners, there's your keyword. Work done by what? The gravitational force on the ball is. And now it goes through, and it's always a good idea to read through questions before you try to answer them. Let's see where they go with this question. They want to know, is the work positive or negative? And they describe points of motion or ways of motion. So what is the issue here? All right, actually very easy, but learners didn't perform very well in this question. Let's draw a ball for you there. There's the ball. And it's thrown vertically upwards. So let's say it goes in this direction. Now I'm going to put a V there to indicate that it is moving upwards. So this is my ball. And as it is going upwards, what forces are acting on the ball? This is something that you must really know very well. And that is how to draw forces on any object. Now, if there is no friction, in other words, if there's no air, then it means the weight will be downwards, and that will be the only force on the object. If there is air particles around this, this ball, then there will be friction in the downward direction because it is going upwards. And I don't want to overcomplicate this, so I'm not going to even put it in. I thought of putting it in, but let's rather not. So, in other words, as the ball is moving upwards, the weight of the ball is acting downwards. In other words, the gravitational force of the earth on the ball is acting downwards. Now the ball goes up, 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 and as all of us know, it goes slower, 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 and eventually stop. And then it comes back again. So let's say this represents the ball on its way downwards. So I'm going to put a V there to indicate that it goes downwards. Now, as all of you know, that as it is going upwards, it goes slower, slower, slower. If it doesn't, it can't stop. So it moves slower, slower, slower. The highest velocity is at the bottom where you project it, and it stops at the top. And then it starts coming down, but it goes faster, 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 faster. So it comes down and it goes up. While it is coming down, what forces or force are or is acting on the body? Well, once again, weight is acting on the body. Small w, né? Weight is acting on the ball, and if you have air around the ball, then the ball will experience a frictional force upwards. In this case, the frictional force will be downwards. But if there is no air, there's no friction, then those two are the only forces acting on the ball. Now, to answer the question, you have to think about the equation for work. Now, work, and this time around, it is now capital W, is equal to the force, in this case, it's W, multiplied by the displacement, multiplied by the cosine of the angle between these two. So it's force times displacement times cosine of the angle between these two. Right. Now this one here, represents where it goes. So in this case, it is up and weight is down. Therefore, for this scenario, the work will be negative because the displacement, in other words, as it is moving upwards, the displacement is upwards and the weight is downwards, so these two are in opposite directions, so the cosine of 180 is applicable here, and therefore, because it is opposite, the cosine of 180 gives you a negative sign for work. So work is negative. When it comes down, displacement
is downwards, and therefore the displacement is now in the same direction as the work. So if you have to do the calculation, the theta is 0, because if something is like this, if something is like that, the angle between the two is 90. If it is like that, the angle is probably 10 now, and if it is like that, the angle is 0. So if it is in the same direction, the angle there is 0, and therefore cosine of 0 is a positive multiplied by positives give you a positive. So in this case, the work done is positive. So which one will be the correct answer? It's positive on its way up. On its way up, it's actually negative, so that part is wrong. And if that part is wrong, it can't be the answer. It's negative on its way up, so this part is a possibility. Negative on its way up, it's a possibility. Positive on its way up, that is not possible. So I have to investigate B and C further. Negative on its way down, no. So that is not right. Positive on its way down, yes. So my answer should be 1.7. What is that? Is it positive on its way up? Positive on its way up. Yeah, sorry. Let me just check. In my preparation, I had these figures the other way around. Look, displacement is up, weight is down. So the work done is negative. So these two are correct. And displacement is down and weight is down. So these two are in the same direction. Therefore, the work is positive. So the answer is actually C. Right. I hope this helps you. A car is moving at a speed V. Yeah, can I just go back to this question once more? I just want to indicate, whenever you do definitions as well, it is important to look at formulae or to think about formulae. When you phrase a definition, it is a lot easier to think about a possible formula that informs the definition. And in this case, we have also demonstrated now that by looking at the formula, you can solve this question. If you can't recall that, you know, opposite directions give you negative work and same direction give you positive work, it is actually important to look at all the tools at your disposal. Right, let's go to 1.8. Let's go to 1.8. This one, the physical science learners will do this one also in the near future. And this is one of those nice ratio type questions. And they are actually very, very easy. I think the mathematics is actually tricking you sometimes. A car is moving at the speed V, and this car has kinetic energy EK. What is the kinetic energy if the speed of the car increases to 2V? Can you see what happens here? V changes into 2V. And now they want to know what will the new kinetic energy of the car be if the previous kinetic energy is represented by EK. So I'm going to write down a bit of mathematics for you here. Perhaps it will help you. We start off by saying the kinetic energy. Now the formula says it is half times mass times V squared. Is this correct? Yes, because they tell us the velocity is V and the kinetic energy is EK. That is the starting scenario. Now you change your velocity to 2V. In other words, we don't have a V anymore. We have a 2V. But the equation for kinetic energy says the velocity must be squared. So it will still be half times m times the velocity, and now the velocity is 2V. This is now my new kinetic energy. Now let's fiddle a little bit with this guy. This will give me half times m times 4V squared. And now you see something familiar. Here is a half, there is a half. There's a m and there's a m and a v squared and a v squared. If I take this, and I have to carry on here now, if I take this 4 and I put it at the front of the following, half times m times v squared. Can you see now this part in brackets look exactly like this part? So in other words, it is 4 times the old kinetic energy, which was called EK. And there it is. And this is the way we do that. You can also say, if you are familiar with this, that, okay, V is now 2V, and the square of 2 is 4, so okay, fine. The kinetic energy must be 4 times as much. But there is a nice way to write it out. The first kinetic energy, or the old kinetic energy, is half mv squared. The new one, and you write it out, you manipulate it slightly, and write it such that you can see this part is the same as this part, and this one is now the factor. And this is actually the reason why speeding is a really big problem. If you travel at 50 kilometers per hour in a car, and you double your speed from 50 to 100, don't think you double your kinetic energy. You actually make your kinetic energy 4 times more. And that is why you can get hurt a lot more at a small increase in speed. In other words, from 100 to 113 kilometers per hour. It feels like it's a few kilometers per hour faster. But remember, it is always the square of the speed that gives you your energy. Question 1.9. Also, not for physical sciences. This one is not at all for physical sciences, so you guys don't need to worry about this one. Which word or phrase describes a body that does not regain its original shape and size when a deforming force is removed? Now, this is the part on elasticity, so it is straight away a plastic body. Now, please, the word plastic, we use plastic in our everyday vocabulary. Don't think about plastic like a plastic bag or a checkers bag or whatever. Plastic in this context means it is something like putty. You have putty or clay or wax. If you press it and you take away the force of your fingers, it will have changed its shape and so on, and it will not go back. While if I have a nice steel thing, and I am, elastic steel, and I press it and I take away the force, then the steel or the plastic ruler, for example, will regain its shape and size. So be careful. I speak about plastic in an elasticity context and a plastic ruler. These things are not the same. A plastic ruler can be elastic, and that is the big thing. So a perfectly elastic body is anything that comes back to its original shape when you remove the force that had changed the shape. And a plastic body is one that doesn't do that. Good examples of plastic bodies are things like wax and a biscuit, for example. If you take a biscuit and you crumble it, it's a plastic body. Okay, the last one, 1.10, also not for physical sciences because this is still elasticity. They have stress. Now remember, stress, the symbol is that little thing, and strain is this little thing. Now, strain and stress, the Afrikaans word for this is spanning and vervorming. Which one of the following quantities represents the gradient of the graph? And I want to just remind you, there are formulae here for elasticity on your data sheet. All of them are there. Learners don't do well in this part, and it's not correct. It's easy. So you must really upgrade yourself there. Okay. The modulus of elasticity, Pascal's law, force and area. Which one of the following quantities represents the gradient? Now, first of all, how do we determine the gradient of a graph? The gradient of a graph is always the change in the vertical divided by the change in the horizontal. So we can say something like that. The change in this one divided by the change in that one. That's your gradient. In other words, if I have a point here that corresponds with a point there, and a point there that corresponds with a point there, then I determine the gradient for this part here. But if it is straight, then each of these points will give you the same value. And therefore we have this formula. Sigma is equal, sigma divided by epsilon, those are the names of those two symbols, that gives you K, and K represents the modulus of elasticity, and it is actually this formula here. Okay, so K is equal to sigma divided by epsilon. It is not Pascal's law. Pascal's law is force divided by area when you deal with pressure. Pressure is equal to force divided by area. But unfortunately, stress is also force divided by area. But remember, this one deals with elasticity. Therefore, force divided by area represents stress, while force divided by area in terms of pressure, then you have Pascal's law. Force obviously and area obviously are not the correct answers. Okay, Bobby, we are going to take a short break now. So, ladies and gentlemen, we will be back at 10:30. It is about 12 minutes from now. So, let's sign off first and be back at 10:30. Thank you very much. Okay, we are back for the second session. You know what? I have forgotten to give you the answer, but I guess everybody is fine now with this explanation. The answer of 1.10 is actually A, because the gradient represents the modulus of elasticity. Okay, let's see how successful we can deal with the rest of the questions in this paper so that we can give an equal amount of time to the physical sciences. Question number 2 is also for physical sciences. So the physical science learners, look at this one as well, because you can also get this type of question. Mpo is pulling a suitcase with a mass of 10 kilogram at a constant velocity. Now, learn that if something is typed in capital letters, it means it is important. She pulls the suitcase over a rough horizontal surface. Now, there are two very important words. Rough means we have friction. Horizontal means it is not at an angle or whatever. It's not vertical, it's not up a hill, it is horizontal, because that affects your mathematics. With a force F of 50 Newton at an angle of 60 degrees to the horizontal. Now, before you even start with this question, you must be prepared to write down certain key concepts or take note of them at least. And the second thing is to draw a diagram, even if they don't ask it. So let's see what they ask. They ask a definition, something about the force, and then calculate the coefficient of the frictional force on the suitcase. So it's probably a good idea to start thinking about the suitcase itself. Right, so on the suitcase, let's look at what is happening here. Before I even answer the questions, let me think about the suitcase. Mpo is pulling it, there's friction, the suitcase has weight, therefore it will have a normal force, so it seems fairly easy to draw the calculations, the forces for the calculations. So let's start answering the questions. 2.1.1, state Newton's first law of motion in words. Now, I don't want to waste time by writing it down for you, so I just want to show you the memo. There it is. An object continues in its state of rest or uniform motion or velocity unless it is acted upon by a net force or a resultant force. So make sure that you have all these words to earn the mark. If you leave out some of these words, you lose at least 1 mark. And you have to memorize these things so that you can reproduce them perfectly. It's a valuable golden opportunity to get good marks. Name the name the non-contact force acting on the bag. Now, before we do that, let's start by drawing a free body diagram of the bag itself. Now, the bag experiences a force exerted by Mpo, and that force, let me represent it with an F, and remember, it is at an angle of 60 degrees to the horizontal. Then, the bag itself has weight, so we are going to put weight there, so that is weight. And because of the weight, remember this technique, because of the weight on the bag, in other words, the gravitational force on the bag is pulled onto the earth. Therefore, the earth exerts a force on the bag, vertically upwards, and that is called the normal force. And Mpo is moving in this direction. It is very clear that she's moving in that direction. So she is going that way. How? Constant velocity. Constant velocity, extremely important. That means acceleration is 0. She doesn't go faster, she doesn't go slower, she doesn't change direction. Constant velocity means acceleration is 0. So while she's walking, there must be something that prevents her from going faster. And that something is called friction. So there's a force of friction on this bag in the opposite direction as the motion. Now, this will be your free body diagram if they have asked it. I do not include any components. It's only the forces themselves. So it's the applied force F by Mpo on the bag, the weight of the bag, meaning the force of Earth on the bag. Because of that, the bag is pulled onto the surface of Earth, and therefore Earth exerts a force on the bag in the upward direction. That is called the normal force. And because Mpo is pulling it to the right, there is a frictional force on the bag to the left. 2.1.2, name the non-contact force. I forgot to switch back, Bobby, my apologies. I forgot to switch back to the diagram, so the learners haven't seen anything that I've shown here. So let me repeat quickly. Constant velocity means acceleration is 0. And then the force is on the back. While she's going that way, the applied force is there, so the dot represents the back. The force of Mpo on the back is this one. The force of the earth on the back is that one. Therefore, the back is pulled onto the surface of the earth. The earth pushes back on the back. That is the normal force. And Mpo is going that way on the rough surface. Therefore, there's a force of friction on the back to the left. And that will be your free body diagram. So if they ask a free body diagram, put down a dot, make sure that the tails of all your arrows touch the dot, put your labels there, and in the case of this now, you don't need to do it like I've done it for the Newton 3 situation. You don't need to say Mpo on back, earth on back, back on surface, etc., etc. You don't need to do that. You can just put F, N, F, and W, because the idea of a free body diagram is that you identify one object, and in this case it is the back, so we know automatically that all these forces are acting on the back. Okay, name the non-contact force acting on the back. Now you can check now, Mpo is touching the back directly. The force of friction works on the back directly. The normal force is the force of the surface on the back, they touch. So the only one that is not directly in contact with the back is the weight of the back. So you can give the answer as you can say weight, or you can say gravitational force. So as you can see there in the memo, gravitational force or weight, any of the two will be fine. Calculate the coefficient of the frictional force on the suitcase. Now learners, remember what I said. If you draw a free body diagram, don't put in any components. But when you do calculations, it is very handy to see the components. So imagine that is finished now. If they've asked a free body diagram, I've drawn it. Now I'm busy with this calculation. Now I put in more things to help me. This force F that is applied at an angle of 60 degrees to the horizontal has a horizontal component and a vertical component. Okay, so I'm going to put the F there, that it just looks a little bit better, and there you have it. So bring the components in to help you. It is really, really very helpful. Because what you can do from, what you can see from here, if there's a constant velocity, it is only possible if the horizontal component of F is equal in magnitude to the force of friction. So you need to know this, you know that. You need to know that. Furthermore, the weight must be equal to the sum of the vertical component and the normal force. If there is no vertical component, in other words, if there's no F, then the normal force is equal to weight in terms of magnitude, but opposite in direction. But now that you apply a force on the suitcase, this force has the vertical component. And therefore, the normal force decreases. You will get questions like that in future. The normal force decreases due to the presence of F, because F has a vertical component upwards, and this one and that one together must be equal to this one. Okay, so that is the situation. Something else that I advocate very strongly is before you jumping in to do the question, try to map out how you're going to solve the question. They want to know the coefficient of the frictional force on the suitcase. Now at the back of the paper, you have your equations. There is the equation. Now this one is a situation where something is moving, so we will probably use this one, the kinetic energy. But even if you don't write the K's and so on, my feeling is they should give you the marks. So this is the argument that we're going to use. The kinetic friction is equal to this coefficient multiplied by the normal force. Now, do I know the frictional force? No, it's not given here. But if I know this one, in other words, that one can be obtained from the horizontal component of F. The normal force plus the vertical component of F plus the weight must together can help me to get the normal force. So I must know something of weight and I must know something of the vertical component. And if you have this and that, you have this and that, and then you can calculate that one because the coefficient is the one that you want to calculate. So, okay, let's quickly do that. So let's start off by this one. And if you look at the memo, you will see for memo purposes, they put everything into as few as possible steps. But there's nothing wrong if you do it one after the other. So first of all, let us calculate the vertical component. So in other words, I'm going to start off by doing the following. Now you have to know a little bit of trigonometry here. The sine of 60 is equal to the vertical component divided by F. Now what is F? Remember, F was given to us as 50 newtons, so it is 50. Therefore, the vertical component is equal to the sine of 60 times 50. Now, I'm not going to calculate the answers, but just to make sure that you know how to do that this once. Sine of 60, you start by pressing, well, you must make sure that your calculator is set on degrees. If it is not, you will not going to get the right answers. So sine of 60 gives you 0.866 multiplied by 50, and that gives you 43.30. 43.30, and I'm just going to include that little 1 so that I have a few more decimals. This is also something important in a question paper. Your final answer, you can round that off to 2 decimals if you like. But for in-between questions, our advice is always to write down at least 3 so that you don't deviate too much from the final answer's correctness. Okay, now can you see now, if I know V vertical, this part is covered. Right, now W is easy because we know W is just the mass multiplied by gravitational acceleration, so that's not necessary to do it separately. Let's now come to this one. That will give you the horizontal component, so the cosine of 60 is equal to the horizontal component multiplied by 1 over 50 or divided by 50, and therefore the horizontal component, now cosine of 60 is the same as sinus of 30 multiplied by 50, and that will give you 25 Newton. Now we are there and we are there. Now we can calculate the normal force, because if I know this, I know that part. But I must still be able to get the normal force from this combination. Now something truly, truly important. In the vertical plane, as I said previously this morning, the suitcase is not going into the earth, neither is it flying into the air. In other words, in the vertical plane, the net force on the suitcase must be 0. In other words, it's not going up, neither is it going down. But what makes up the net force? And now I'm going to teach you something that I referred to this morning. Think back about our vectors. Remember when I drew these things? This vector plus that vector gives me this vector, and this one is called the net, and those two are called the components. Now, very much the same thing. If I have vectors in opposite directions, I still add them, although some are negative. And therefore, this one added to that one gives me this one, and this one is my net vector. So I have to add vectors. There's not something called subtraction of vectors. We always add vectors. So first of all, let's write down the symbols that represent the net force. Okay, the net force in the vertical plane, it's the normal force plus, can you see I put a plus, the vertical component plus the weight. At this point in time, I don't fiddle with negatives. This is the mathematics, in other words, addition of vectors. Now I'm going to choose a direction and substitute. And what is important now is if you choose upward as positive, it's going to look as follows. The normal force is the one that I want to calculate. What is the vertical component? There it is, 43,301. And listen how I speak now. The magnitude is 43,301. This is the magnitude. What is the direction? It's upwards. What did I choose upwards? Positive. Therefore, this number must be substituted as a positive. In fact, I'm going to emphasize it. You don't need to do this in the examination as that. But this plus is my operator, and that plus indicates direction. You could have written only plus 43,301. That's fine. But I want you to realize why we do it like this. Now I write down that plus. There it is. Now I come to weight. Now weight is the product of mass times gravitational acceleration. What is the weight? Sorry, what is the mass? The mass of the suitcase is 10 kilogram. So there is the mass. And gravitational acceleration is 9,8. So listen how I talk now. The magnitude is 9,8. What is the direction of gravitational acceleration? It is always downwards to the center of the earth. It is always downwards. I've taken up as positive, therefore I need a negative here. And this now will give me the negative value for the weight, because weight is down and I've chosen up as positive. And that is all equal to 0. So what you have now is n is equal to, now on this side it's negative 98, so I add and add on the other side, so I get a 98. And this one is a plus, so I must subtract 43,301, and when I do that, I get 54,7. Let me just check this one. 98 minus 43.301, and that is 54, and I want to show this to you, 699. And that is why, you know, we can actually say 70 if we like to. So N is so many newtons, 54,7 Newton. Now I know this part. Once I've done that, I can now come and I can say, okay, the kinetic friction is the coefficient of friction multiplied by the normal force. And the frictional force is the same as the horizontal force. Now something here that is maybe a little bit confusing. The horizontal component is to the right, it's 25. It's 25. So the frictional force is to the left, therefore if that one is positive, then this one is negative. So what I advise you to do is, before you come to this step here, in other words, after this part here, write down the following. You have done that part. Then you can say the frictional force is equal to 25 Newton to the left. Because you know Moss, it is the same as the horizontal component because there's constant velocity. Right. Now when you substitute in this equation, you can use only positive numbers because this is not important in terms of directions. Friction and normal are always perpendicular or normally perpendicular. So the frictional force, you can just substitute a positive 25, or any time you substitute here, you can use positive numbers. And the normal force is 54,7, and therefore the coefficient of friction is equal to 0,44 without a unit, because it is just a coefficient. And there is your answer in completeness. When you go to the memo, you will see that they put in things in less detail, but to do well in this type of question, I suggest you can break it up in little sections. First, the vertical component, the horizontal component. From this, you know what is your frictional forces, magnitude and direction, obviously. After that, you have to calculate the normal force, and the old story is the normal force plus the vertical component must have the same magnitude as this. And there it is, and once you have done that. So this is fairly complicated, not complicated, but in a way it is, let us say, a little bit challenging, but not undoable. All right, let's fire away. There's many questions to come. John with a mass of 70 kilogram and Mary with a mass of 50 are standing on an ice rink as shown below. Now, instead of an ice rink, you can have roller skates as well. The idea is to bring into the question the idea that we don't have a lot of friction. Then John pushes Mary away with a force of 50 Newton to the right, and they glide away from each other. What is the direction and magnitude of the force experienced by John? Now here again, I think it is not a bad idea to indicate your forces. Now just to practice, on Mary we have a weight. Now John pushes on Mary, so this is the force, and I'm going to put it like this: John on Mary. Therefore, the same force is applied to John, but this time it is Mary on John. Okay, John has a weight as well. Sorry, the arrow doesn't come out so well on the colored trousers of John. Now, because of the weight, the gravitational force, both John and Mary are pulled onto the ice ring, so the ice ring is applying a force on them. So there's an upward force normal on John and an upward force normal on Mary. Now, obviously, if Mary's mass is less than John's mass, the weight of Mary is less than the weight of John, therefore the normal on Mary is less than the normal on John. Right, now that is the force applicable from the moment John touches Mary. In other words, I hope you can see my hands. Let's say the two fingers represent John and Mary. If they don't touch, these two forces do not exist. It is only from the moment they touch, and then John pushes. But as he pushes on Mary, Mary is actually pushing on him. And therefore, while they are in contact, they push each other away, and the moment they break contact, then these two forces disappear again. These two obviously remain. And if we assume that there's zero friction, then there's no other forces on John and Mary. But because of this initial push, they now move this way and that way. That is the direction of the velocity of Mary and the direction of the velocity of John. And now they ask, what is the direction and magnitude of the force experienced by John? By John, in other words, the force on John, while he, pardon me, is pushing against Mary. Now here it says, John pushes Mary away with a force of 50 Newton to the right. Then this force on John is 50 Newton to the left. That is then the force on John. 2.2 is a tricky question. Not so much in understanding it, but in terms of presenting it to the marker or to your teacher. Explain in terms of inertia. So you have to say something of inertia and other applicable concepts. Why John and Mary could not cover equal distances from their starting points. In other words, which one is going further from the starting point? Will John go the furthest, or will Mary go the furthest? Let us deal with that situation a little bit, because this is very, very important stuff. Now, point number one. John has a mass of 70. There you can see that. John has a mass of 70 and Mary has a mass of 50. In other words, in terms of magnitude, we can say the following. The mass of John is greater than the mass of Mary, because that is given to us in the question. Now, mass represents inertia, and you can think about it as follows. If you have a small car compared to a big bus, and both are stationary, it's going to be much heavier to get the big bus moving when you push against it than the car. So therefore, we can say inertia of John is much more than the inertia of Mary. Now we've covered this part, because I've said something about inertia. But now I must explain to somebody why they can't cover equal distances. Now let's go through the mathematics and the physics of this scenario. Remember, they touch each other, and we know the forces are equal. So this force is equal in magnitude to that one, but opposite in direction. The moment they break contact, the forces disappear, but at that point they are moving already. And from the moment they touch until the moment they break contact, these two accelerate. In other words, they are stationary and then they are moving. Between these 2 points, they accelerate. Mary to the right and John to the left. The moment when they break contact, from that moment onwards, they will move at constant velocities. So, let's see what happens. Let's look at F net equals ma. Because we know that during the acceleration, this is the net force on John in the horizontal direction and the net force on Mary in the opposite direction. And we know the force of John on Mary is equal to the force of Mary on John. Remember, I've written here in terms of magnitude, né? So I just compare magnitudes. The forces are actually opposite in direction. Now, higher up we have said John has a higher mass as Mary. Now, the one with the larger mass for the same force will have the smaller acceleration. So the acceleration of John will be less than the acceleration of Mary. Why? Because the force is the same on each one, but John has a higher or a greater mass than Mary, therefore John has a smaller acceleration. And if John's acceleration is less than the acceleration of Mary, then it means Mary will have a lower speed by the time they break contact. The speed of John, Mary will have the higher speed. The speed of John will be less than the speed of Mary when they break contact. And now you can think, né? If you take the distance for 1 second each, then the distance covered by John will be less than the distance covered by Mary. Now, if you succeed in writing down this part here, you have given more than enough physics to explain to them why they cannot cover the same distances. Quite complicated, but try to do that. Answer the question the way they like to. I have referred to inertia and other applicable concepts. Now, what are the other applicable concepts? Well, forces. And the moment when we deal with forces, we must think of masses and acceleration and velocities and so on. And I've written it down in a mathematical way. You don't need to write long sentences, etc. And I also try to keep the same stuff on the same side. So I talk about mass of John, mass of Mary, inertia of John, inertia of Mary. This one is difficult. You can probably swap that if you like to, but doesn't matter as long as we know it is the same. And acceleration of John, etc., etc. So the acceleration of John and the acceleration of Mary. Okay, so I hope that helps you. These explanation type questions are sometimes a little bit tricky, but there's no need that you need to be afraid of them. Don't write too long sentences. Sometimes learners start off writing the same thing or actually the correct thing, and then started to write more and more, and then they start to say, in other words, therefore, blah, 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 and sometimes they start to contradict themselves. So think about what you want to say and say it in the shortest possible, most clear way. Right, question number 3, physical science learners, you can also look at that. And by the way, this one is a very good physical science question as well. Right, 2 blocks, M and N, with masses of 5 and 3 respectively. This thing of respectively, we must just make sure that you know what that means. It means the one that comes first is first, the one that comes second is second. So 5 is the mass of M and 3 is the mass of N. Are connected with a string of negligible mass. In other words, there's no mass there. A horizontal force F is applied to the 5 kilogram block. Now check this situation. The 2 blocks are connected with this string and put down on a surface, and then a horizontal force is applied to the 5 kilogram block. That's important. In other words, this force is acting on M only, not on N. Both blocks accelerate at 2, so they move in this direction, and the acceleration is 2 meters per second squared. Please note, I don't say -2 or +2. I just say 2, meaning the magnitude is 2 and it goes to the left, because that is what they tell us. Frictional forces of 12 and 8 act on the 5 and the 3 kilogram block. Right, we'll come back to that. Then they asked Newton's second law, calculate the magnitude of F, then something about the string breaks, etc., etc. So if I scan through this, and that is what you must do in the exams, it seems to me we are in for force diagrams. So let's draw force diagrams. Right, first of all, F is applied to this guy. Then M has a weight, so I'm going to put a weight here. Don't worry about the comparative magnitudes of my arrows. I just want to bring these things in for you. Now, once again, the weight causes the block to press on the surface. So the surface presses on the block, and therefore we have a normal force there. Then here they say frictional forces of 12 and 8 act on 5 and 3 respectively. So 5 kilogram, this one, experiences frictional force of 12. Now let's put it there. This is the frictional force on M. Sure, I hope I have enough space for this. This is 12. And there's also a frictional force on block N. Let's put that one in here. So there's a frictional force on N, and this one has what is that? 8 Newton. Okay, that's 8 Newton. Furthermore, this one has a weight. Now remember, this one is 3 kilogram. This one is 5 kilogram. Righto, therefore this one's weight is more than that one's weight. There's a normal force. And now the big thing. How do we succeed in pulling this guy? It is because the string that connects the two, the moment when M starts to move, the string cannot stretch. Therefore, this point of the string exerts a force in this direction on the 3 kilogram block. And therefore, it goes this way. Now, any force that the string exerts on a block, we normally just call it T, because it is the force of this end of the string on the block, but all the little fibers, and that is something I've tried to explain in the previous video that we have made earlier this term, the fibers carry the force forward. So on this side, this end of the string exerts a force in this direction on the 5 kilogram block. So there you have all your forces. It is the weight, the normal force. In a horizontal direction, the applied force, the frictional force, and the tension, or the force of the string on this block. And this one has weight, normal force, tension, and the tension causes this block to follow the 5 kilogram block, and to the right you have a frictional force. Okay, so there are all the forces. Even if they don't ask it, put it in and make sure that you know that. Right, state Newton's second law of motion in words. Very important here, just a reminder once again. You have to remember to talk about a net force. If you leave out the word net, you lose a mark, because Newton's second law depends on two parts, and it is something that irritates me terribly with with technical sciences. The first part says the net force accelerates the object in the direction of the net force. Né? So there you can see the first part. When a net force is applied to an object, the object accelerates in the direction of the net force. That is the first part. Then the second part tells you the relationships between these things. And it comes down that acceleration is directly proportional to the net force, and acceleration is inversely proportional to the mass. And it is from there that we have this equation, F net is equal to ma. In other words, the heavier an object is, the smaller the acceleration is for the same net force. Or vice versa, for the same mass, the stronger, the higher, the greater your net force is, the more your acceleration is. And for technical sciences, unfortunately, they have only included one part here. Acceleration is directly proportional to the force. Up to there is what you normally see in textbooks and stuff. But my advice is add this part here. It says acceleration is inversely proportional to the mass of the object. Check. Acceleration is inversely proportional to the mass of the object. And the first part, this part here, acceleration is directly proportional to the net force. These two are very important for the complete Newton's second law of motion. It is better that you put it in that way. So follow the memo in this case and not your textbook. Right, 3.2, calculate the magnitude of force F. So once again, you can come up with a little scheme and say, okay, how can I calculate the net force or force F? Ne? I calculate force F. Now I think everybody realizes that we are busy with Newton's second law of motion, so it will be F net ma. Let's see, do I know everything that I need? I want to calculate F. So in a horizontal plane, F must be part of the net force. So F is definitely here, but that is the one that I want to calculate. What else do I have in the horizontal plane? Well, I have tension. Do I know tension? Not at this stage. In the other force in the horizontal plane is the force of friction. Do I know that? Yes, they give it to me. They have said it's 12 Newton. So I have no other forces in the horizontal plane than these. Then what else? Do I know the mass? Yes, they've given the mass. Do I know the acceleration? Yes, they have given me the acceleration, so I have that. So I can calculate F provided I know this one. Because if you have two unknowns, you cannot solve an equation. Now the question is, how am I going to get T? So let's look at the other body. For that other body, I also know M and A. And for this guy, in this case, T and F are my two horizontal forces. And I know F. So it seems to me that I have everything I need. For the horizontal net force, I have T and F, of which that one is known and this one is unknown. And I know M and A, so I can calculate this one. And once I know T, then this T is the same as that T. It is just that the direction is opposite. So based on this argument, we have to start with a 3 kilogram block. So let's do that. Let's do that. I just want to move this up a little bit. Okay. So for my 3 kilogram block, first thing, write down your basic equation. F net is M times A. Now I write down the vectors that make up F net. And in the case of the 3 kilogram block, it is T plus F, and that is equal to M times A. Now I'm going to substitute, but before I do that, I have to choose a direction. Now, whenever you deal with Newton's second law of motion, it's always a good idea to take the direction of the acceleration as your positive direction. You can do it any way you want, but that's an easy way to solve your questions. Okay, what do I want to calculate? T. So T plus, once again, learners, I keep on hammering on this because this is easy stuff to get marks. That one is my operator. What is the force of friction? 8 Newton. Listen how I talk. 8 Newton, what is the direction? To the right. And I've taken to the left as positive. So this one is negative. And that is equal to, what is the mass? 3 kilogram. And what is the acceleration? The magnitude, listen how I speak. The magnitude is 2. What is the direction? To the left. I have chosen positive to the left, so this one must be a positive 2. You don't need to put in that 2, but you have to put in that negative. Okay, so from this it's easy to see that this is 6 and this is minus 8. To get rid of minus 8, I add 8 here and I add 8 there. So it will be 6 plus 8, and that will be 14 Newton. Now, very important, this 14 Newton is to the left, né? Because can you see, it ends with a positive answer. Positive is to the left, so force of rope, is it a rope or a string, doesn't matter, on the 3 kilogram body is 14 Newton left. Here I have now interpreted my answer. Okay, now I go to the 5 kilogram block. 5 kilogram. Once again, start with your basic equation. F net is equal to MA. Now, which forces do we have here? You can't see everything on the screen, so I'm quickly going to put them in. It is the applied force plus tension plus the frictional force, and that is equal to MA. Now, let's keep on using this decision of us. So I want to calculate F plus, and here comes the catch. Remember, the force of the rope on the 5 kilogram is to the right. In other words, it must have a negative sign, and the magnitude is 14. It comes from there. Right, that is very important. Plus, plus. The friction is 12 Newton. The magnitude is 12. The direction is to the right, so it's negative 12. The mass in this case is 5. The magnitude of acceleration is 2. What is the direction of acceleration? To the left, therefore it has a positive. That positive that I've put there, I said you don't need to do that, but remember it's positive in this case. Nah? So sometimes people like to put that. Okay, so 5 times 2 is 10. On this side I have minus 14 and minus 12, which is minus 26. Add 26 both sides, so you get plus 26, and then you have F. And F will then be 36 Newton. Now we must check the question. They want to ask, calculate the magnitude of force F. My advice is write down magnitude of F is 36 Newton. Write down this step for them, because sometimes in the memoranda they like to have that. Now, what would have happened if you've chosen negative to the left, in other words, positive to the right? Then this part would have remained the same and the same. So the friction would then become positive there, and very, very, very important, this one would have become negative. Né? So therefore, you would have got negative 6, and on this side it's negative. Let me just check now. Wacht. The frictional force is to the right, so that would have been positive, and the acceleration is to the left, so it would have been negative. So it would have been a negative 6 here, a negative, a positive, and on this side it would have been a negative, and then this would be a negative. So it's only this part that would have changed, because the force on the rope would still be 40 Newton magnitude, and being negative means it would have been to the left. Then in this case, this part up to there remains the same. So the T is now to the right, so that would become positive. The friction would become positive, and the acceleration would become negative. Now it would have been a negative 10, positive 14 and positive 12 would have been, to get rid of them, you would have subtracted them on that side, so you would have got a negative 36. And that is why I say it is perhaps a good thing, because if they've asked you the force itself, in other words, if the question was calculate the force of F, then you would have said the force in your interpretation, the force is 36 Newton to the right, to the left, okay? To the left. In other words, with a pencil ending in a positive, it means it's to the left. So if they've asked now, it's important now, calculate the force, then it means you have to give the answer in terms of magnitude and direction. Then you would have said 36 Newton, separate from the calculation, 36 Newton to the left. If you have chosen positive to the right, then you end here with a negative 36 Newton. So if they asked the force, then you would have still said the force is equal to 36 Newton to the left. But now they've asked magnitude, and therefore, irrespective of what you have here, a negative or a positive answer, put in a separate step to say magnitude of F, and then give the answer. It is just a good trick to write examinations, because sometimes they put a mark on the fact that they want to see, do you know what is the magnitude of the force, especially when you end in a negative answer. And this is also valid when you calculate things like height and speed and so on. Right, 3.3. Calculate the string between the two blocks break. while all the other forces acting on the 5 kilogram block remain unchanged. Now, what you can see obviously is when the string breaks, then this one is going to disappear. And now they say draw a free body diagram of all the forces acting on the 5 kilogram block. Now, to save time, I'm just going to show you the memo because I'm not going to write down everything for you, but I like to explain as I write. But in 3.3.1, that is your answer. You don't have your tension anymore there. You just have your friction. So if you come back here, the friction remains, but the tension disappears. The weight and the normal remains and F remains. So there's the answer. 332, calculate the magnitude of the new acceleration of the block. Now, the nice thing now is, if you go to 3.3.2, by then you know the force on the front block is 36 Newton. Eh? That is basically easy. So F net is equal to m times a. So let's choose to the left as positive. And once again, F net is made up by F plus friction, and that is equal to m times a. We know F is 36. Just check the directions now. The magnitude is 36. The direction is to the left, and I've chosen to the left as positive, so this must be a positive. That plus is my operator. The friction is, the friction on the 5 kilogram block is, what was that? That was 12, no? Let me just check. Yeah, it's 12. The magnitude is 12, but it's to the right, so it must be negative. And you see, if you can change these things and write them out correctly, you can really do very well in your question papers. The mass of the block is, what was that? 5 kilogram. And the acceleration of the block, the magnitude is 2, but it is to the left. Sorry, that is what we must calculate. My apologies, I almost forgot. It is after the string has broken. So that is the acceleration. So I have a positive 24 on that side and a 5a, and therefore it will be 24 divided by 5, and that is a. And a will then be positive 4,8 meters per second squared. Now let's check the question again. They say calculate the magnitude of the new acceleration. So they don't ask the direction. If they've asked the direction, you would have said here, acceleration is 4,8 meters per second squared left, because this positive refers you to left. This is now the interpretation if they've asked you acceleration. But now they ask you the magnitude of the acceleration. So I think it's a good idea. Write out magnitude of acceleration is 4,8 meters per second squared. The reason for this is if you've chosen to the right as positive, then these signs will be different and you will end up with a negative 4,8. And they might want to test, do you know what it means? And 3.3, what happens to the 3 kilogram block immediately after the string has broken? Give one reason. Now there are various reasons, and this is very, very, very nice physics, because the moment when the string breaks, there's no more a T or a force of the rope on this 3 kilogram block that pulls it forward, but there's still a frictional force. In other words, by then, this block has reached a certain speed, and now you remove this force. So from that moment onwards, it will move slower. So they say, what happens to the 3 kilogram block immediately after the string has broken? Immediately after it has broken, the block will move slower until it stops. And why? Now you can give many examples. Now there's your memo. 3.3.3, the block's speed will decrease until it stops. Now you can give a lot of examples. What I like is the one that says the net force. Remember, if you look at your diagram, when you remove this horizontal force T, then the only horizontal force is the force of friction. So that guy is actually now the net force on this block. And the block is, at that moment when the string breaks, the block is moving in this direction at a specific velocity. But it experiences a net force in the opposite direction. And therefore, it's going to slow down. So one reason would be that the net force is in the opposite direction as the motion, and therefore it will slow down. Another reason is just to say there's a frictional force in the opposite direction than the motion. So any way that you deal with that will be acceptable. All right, Bobby, we still have a few minutes time for this session now. I really hurry to get through everything. I think I will have to be a little bit selective with my writing, otherwise we will not have enough time for the physical sciences. But in any case, we'll do our best. Right, let's see, how complicated is question number 4? Now, question number 4, physical science learners, you must also do this. In other words, so far, we have all questions applicable to physical sciences as well, except those questions on work, energy, and power. That was not part of physical sciences in term 1, but it will soon become part of your thinking as well. Okay, a girl on roller skates, total mass 50, moves at a velocity of 6 to the left on a horizontal surface. She catches a ball, mass 450 gram, thrown at her at a horizontal velocity of 0.42 meters per second. As shown in the picture, ignore the effects of friction. Okay, I think for the sake of quickness, let me show you the memo in the case of this one. This is a fairly easy question. 4.1.1, the definition. We can move past that. Please just make sure that you have all those words. Then they ask the momentum of the girl before she catches the ball. Now, this is quite important. Remember, it's a nice sketch here. The girl has a mass of 50 kilograms, so it's always good if you write your material into this thing. Moves at a velocity of 6, and you can see it's to the left on a horizontal surface. In other words, there's no components involved here. She catches a ball, mass 450 gram. Now, there's a problem because it is given in gram. Let me just put this on the screen. It's given in gram, and we must work in basic SI units, so it must be 0.450 kilogram. Now, technical science learners, conversion of units. Mrs. Altafourie has done a lesson for us on conversion of units. You have to be able to do that. In the physical science paper, we also have conversions of units, but it is just built into the questions. In the case of technical sciences, we have a specific section that deals with conversion of units, and it is really important that you be able to do that. Okay, so the ball moves in her direction at a velocity of 0.42 meters per second. And now they ask, calculate the momentum of the girl before she catches the ball. So it's actually this part that's applicable there. I have to save a little bit of time to go through this. Okay, so there is your momentum. It is just P times V, choose a direction and put in the values. Then 4.1.3, they are state the principle of conservation of linear momentum. Important, when you see a little line like this, it is important that you realize if you miss any of these words, you lose the mark. It must be the total linear momentum of an isolated system remains constant in magnitude and direction. Then 4.1.4, calculate the velocity of the girl after she has caught the ball. Now remember, now you bring in this thing, and I'm trying to save time by just showing it to you. Just be careful. It must be, that is the mass of the ball. Can you see? We have converted it to kilogram, and the velocity of the ball, 0.42 meters per second. Now, if you take to the right as positive, these two must be positive. The mass of the girl and the velocity of the girl, -6, né? And then on this side, just be careful, it is the total mass of the ball plus the girl. The total mass of the ball plus the girl. Now this plus that give you a mass of 50.450 kilogram. And in the memo, it will be corrected for the memo. It was just a typing error. It must be 50.45. That 42 must be 45. Okay. And that then is the answer to this question. The next one I will write out for you again, because the next one is a nice question. a hockey ball with a mass of 0.2, let's write this out. A hockey ball with a mass of 0.2 kilogram moves to the right at a velocity of 10. So there's the ball, and it moves in this direction at, okay, so it's 0.2 kilogram, and it moves in this direction at 10 meters per second. A player hits the ball with a stick, a hockey stick, in the opposite direction. So now the ball changes direction, and it comes this way. The magnitude of this change in momentum, careful here, the magnitude of the change in momentum is equal to 3 kilogram meters per second. Now, this is probably the most important arrow for this morning. Because if I have a ball moving in this direction and I hit it with a hockey stick, obviously it must go in this direction. This is not such a familiar question to many of the learners, and directions are your biggest enemy here. So, first and foremost, 4.2.1. Write down the magnitude and direction of the impulse exerted by the hockey stick on the hockey ball. Now, I think everyone knows that if you want to move the ball that is initially going in this direction, and you now want to have it going in this direction, that you must apply a force in this direction. And the net force is the one that we refer to. So if you think about your equation, F net delta T is M delta V, as I said earlier, this is delta P. So if the net force is to the left, then the whole thing here is to the left, If the net force is to the left. Righto, because the ball is moving to the right. And if impulse is to the left, then change in momentum must also be to the left. And this is why I've put this arrow here, just to give you an indication, the momentum change. In other words, the changing momentum or the change in momentum is to the left. So write down the magnitude and direction of the impulse exerted by the ball. What have they given you here? They've given you change in momentum. So to answer the first question, the impulse is represented by F net delta T. But impulse is the same as change in momentum. Therefore, the magnitude is 3 kilogram meter per second. And the direction must be left. So there is your answer, is 3 kilogram meters per second to the left. Sorry, not there it is at the bottom. In other words, 3 kilogram meters per second. I just saw in the memo they prefer this unit, obviously. I should have written it. So it is Newton times second, although Newton second is the same as kilogram meters per second. People should not mark you incorrect if you use kilogram meters per second. Okay, left and 3. Now, the reason why that is important is because if you calculate the rest of the stuff, it is really going to help you if you have a correct impulse. Okay, now they ask in 4.2.2, calculate the magnitude and direction, can you see, both of them, of the net force exerted. So, F net times delta T equals M delta V. Now it depends. If you, for example, choose, and remember to write down these type of things in your answers. For every calculation that you do, indicate to the marker what you choose as your positive direction. Now, F net delta T, therefore, F net multiplied by the 0.3 seconds is equal to the mass. Now, the mass of the hockey ball is 0.2 kilogram. And change in momentum or change in velocity, do we know that? Do we know that? What are we doing with this thing now? What do they ask? Calculate the magnitude and direction of the net force. Is it necessary to write it like this? Is it necessary to write it like this? Not really, né? Because you can easily, I mean, this part is the change in momentum, and they've given it to us, so it's not necessary to write it like that. We can just say it is 3. But the important thing now is the direction must be correct. and the change in momentum is to the left, and to the left I have taken it as positive. So therefore, it is F net times 0,3 is just equal to 3, because we don't need to put in the change in velocity. So therefore, F net is equal to 3 divided by 0,3, and that will be 10 Newton. Now that's the end of your calculation. Now you must interpret that. So therefore, F net is 10 Newton left. It is really important to do this separately. Why? Because if you have chosen to the right as positive, check what happens now. Then this will remain the same, but this one would have got a negative sign. Therefore, this answer would be negative. And from negative 10, you would have still interpreted it like this. F net is 10 Newton. The negative means to the left. And that is really, really, really important that you be able to do that. 4.2.3, calculate the speed of the ball after the change in momentum. Okay, so now I have everything I need. I can calculate the speed of the ball very easily. Remember, you were given delta P, and delta P is m v final minus v initial. Let's keep this choice for the positive direction and show it in your answers. So the change in momentum is 3 to the left, so it will carry a positive sign. The mass, now here comes the mass, which is 0,2. The final velocity is what we want to calculate, minus. Now this minus is an operator. What was the initial velocity of the ball? It was 10 to the right. So the magnitude is 10. Left is chosen as positive, so right must be negative. So I hope you follow my advice. That one is an operator. This one is the sign. So I have 0,2 times Vf. A negative times a negative is positive, times this positive will give me 0,2 times 10. That will give me a 2. So 3 is equal to 0,2 Vf plus 2, and therefore Vf will be the following. Now I subtract the 2 there, so it's 3 minus 2 divided by 0,2. So it is 1 divided by 0,2, and that will give you, I think, 5 meters per second. Let's just check. It's a positive, né? So the final velocity is 5 meters per second. Positive. That positive is to the left. And if they've asked that, then you can also indicate what is the direction. Although, look at the question, calculate the speed of the ball. So if they've asked you the velocity of the ball, you would have given this part. If not, like now, indicate speed is 5 meters per second. Once again, why? Because if you have chosen positive to the right, then this one would have been a negative, and that one would have been a positive. Am I right now? Yeah, the initial velocity was to the right. So you would have ended up with a negative 3 and negative 2 there, and you would have ended up with a negative 5. And from a negative 5, that would have still been your interpretation, and the speed would still be a 5. So I hope this will help you a lot in dealing with this one. Bobby, I know we are supposed to go, but can we stretch this unit a little bit further? Will that be fine with you? Okay, learners, Bobby is willing to carry on because I do not want to neglect the physical sciences too much. So Bobby, thanks a lot for that. So let me quickly rush through this one and just touch on the most crucial aspects of question number 5 for the technical science learners. The issue here is work and energy. So I just want to come to one or two things that are important, because this question 5 is basically very, very straightforward. So if I can deal with question 5 and 6 quickly, then I have finished technical sciences, and then when we come back at, what time, Bobby? Is it 2 o'clock? No, at 2 o'clock. When we come back at 2 o'clock, we can then start straight away with physical sciences. But I hope the physical science learners have gained a lot so far, because the rest of the stuff that we are going to do now, this specific question 5, you will have to do that in the second term. You are going to do work, energy, and power. Question 6 is not at all for physical sciences, so you can relax when I do question 6, but you can actually look at this one for the sake of knowing these things from next term. Okay, let's quickly go through this, and I'll write as little as possible here. I just want to point out a few things. While rushing to an accident scene, a police officer applies the brakes of his car at point A. The car stops at point B. The combined mass of the police car and the officer is 800 kilogram, and the distance between the 2 points is 88 meter. The total force of friction on the car is 32.92 Newton. So if you draw forces for the car, then once again, I think this morning we have demonstrated enough how important it is to have all these forces. So small v for weight, then the normal force. Now, why is there a normal force? Because the weight of the car, or another word is the gravitational force of the earth, pulls the car onto the surface pushes onto the car. I have repeated it now perhaps 6, 7 times. If you make a mistake with this, it is not my fault or your teacher's fault. It is now your fault, because you have to take responsibility for your learning as well. And it is easy stuff, this. So please make sure that you do this correctly. And if you don't understand, you are 100% and always welcome to ask us again. We will help you again and again and again, so that you get success. We really care about our learners. Right. Now, when you brake, there's no more propelling forces on the car, so you just have a frictional force on the car, and that will be your force diagram. And if you draw a free body diagram, the whole story of the dot and the arrows and so on. Numbers 1, 2, and 3 represent different forces acting on the car. Define the term work. Okay, fine, it's in the memo, go and study that. Identify the forces labeled 1, 2, and 3. Now 1 will be the normal force. Okay, because it says here, numbers 1, 2, and 3 represent different forces acting on the car. So 1 is the normal force. 3 must be the weight, and 2 must be the friction. And they have given it here for you, so you can actually come in here. And when you get the memo, we will publish the memo on the website very soon. So 1 is the normal force, 2 is the frictional force, and 3 is the gravitational force, or the weight. Calculate the work done by the frictional force. There is the formula for work at the back of this paper, capital W. The formula for work says it is the force, in this case it's then frictional, multiplied by the displacement. In other words, we can say delta x, multiplied by the cosine of the angle between these two. Now it is so important. Can you see F is to the left? The direction in which it moves is this direction. Delta x is in that direction. And if you have two things opposite in direction, cosine of theta is 180 degrees. Now here I want to please ask you very kindly. It is so important that you remember this. This formula, the way it is structured, includes a cosine of theta. And that cosine of theta takes care of the directions of the forces. So in this specific formula, you never think about including signs with numbers. In other words, this part will deal with your numbers, and you will deal with your directions. In these two variables, doesn't matter if it is up or down or left or right. The mathematics of this thing requires you to substitute positive numbers into this equation. So F must become 32.92, but only positive. And the delta x is the 88, but only positive. And the reason is cosine of theta takes care of the direction. There's a little bit of mathematics that we don't explain now, but when an equation is like that, the cosine of that angle will take care of your directions, and all you need to take care of is it's either 180 if it's opposite, or 0 if they are in the same direction, or maybe if they are in a direction like this, then let's say the force is in this direction and the motion in that direction. If this angle is 30, then you put in cosine of 30. But the force and the displacement must always be substituted as positive numbers. Okay, then this one is a girl, mass 22 kilograms, standing on a garden wall. Standing on a garden wall, what does that mean? Kinetic energy is 0 at the top. She jumps from the wall, which has a height of 1,5 meters. So potential energy is mgh, and the h is 1,5 meter. And the mass is given, so you know this part and you know that part. State the principle of conservation of mechanical energy. Okay, fine. How much kinetic energy has the girl before she jumps? It's more 0. And use the principle of conservation of mechanical energy to calculate the speed of the girl when she hits the ground. So all you need to do, very, very straightforward, this one. You start off with your formula. The sum of mechanical energy at the top is equal to the sum of mechanical energy at the bottom. Now at the top, the potential energy part is m times g times the height. And remember again, in this calculation, we also don't put in any signs, all of them positive. There is the 0 at the top. Now at the bottom, when she's at the bottom, if the bottom is your reference level for the 1,5 meter, then it means potential energy at the bottom is 0. Plus half times same mass, it's the same girl, and v squared, and you just come up with the answer. Okay, I'm rushing a little bit, but the important part here is you can look up these things in the memo. Okay, so Bobby, just 5 minutes or so, will that be okay with you? Very well. Question number 6, not for physical sciences, remember? It is a question on elasticity. Actually, an amazing piece of work. I love elasticity, and it has a major application in the real world. One or two things I want to point out for the technical science learners, and this is the part where you mess up your marks. It's unnecessary. You can really get all the marks. First and foremost, remember, all your elasticity formulae are here. As I said earlier, this one is for the extension and so on, so we call it strain. This one is stress, the force divided by the area, and this one is the division of this one and that one, one by the other, to get the modulus of elasticity. The big thing here, and that was also something that came up in last year's question paper, the big thing is you make mistakes when you convert numbers between the different metric units. Now just one let me say one easy way to remember that. Let's say you have to convert millimeter to centimeter. Now, the first thing that you must know is what is the factor between the two. Now, what people sometimes do is they do this kind of thing. They say, if we work with distances or lengths, they say meter is the standard unit. Okay, so the standard unit carries 10 to the power 0. So for 1 meter, what do you have for the rest? And then you build them up for those that go bigger, and you build them up for those that go smaller. So let's go this way for bigger. Now, kilometer and kilometer, né? Kilometer. What is the factor between these three? Now, I have a tendency of say, just remember that the factor is 10 to the power 3. In other words, a kilometer is 1,000 times more than a meter, or a meter is 1,000 times less than a kilometer, because the positive or the negative is determined by what you convert into what. If you go smaller, 1,000 times smaller than a meter is the millimeter. But for normal measurements, we often use something called centimeter. Now, a centimeter is 100 times smaller than a meter. So the factor from meter to centimeter is actually 10 to the power 2. And from meter to millimeter, it is 10 to the power 3. Therefore, from centimeter to millimeter, it's 10 to the power 1. Now, this is not a nice scheme now, but let me do 1 or 2 examples. Let's say I have 10 centimeter, and I want to know how many millimeter it is. And Mrs. Fourie has done a complete lesson on this. So I am actually repeating here. Right. So what you do here is, first and foremost, you go and check where you go. Now, you are measuring in centimeters. Now, a centimeter is about this distance. Everybody knows what a centimeter is. It is about that distance between my fingers. While a millimeter is very small. So if you go to that centimeter, millimeter, the unit that you measure in becomes smaller. Then the number that you use must become larger or greater. In other words, it is 10, that's my original number, multiplied by the factor. And now you must just know the factor. The factor from centi to milli is 1. And to make it larger, it's a positive. That's how I do that. In other words, 10 centimeter is equivalent to 100 millimeter. And that's the way you go. Right. 1 kilometer. 1 kilometer. I want to know how much meter is it, how many meter it is. Okay, now I go from kilometer to meter. So my unit becomes smaller. So my number, if I measure in smaller parts, I must have more of them to measure the same thing. So my number must become greater. I think I should have said here greater. I think that is better English. Okay, now you must think of the factor. Kilometer and meter. Meter and kilometer, the factor is 10 to the power 3. So I take this number, 1, multiplied by the factor. The factor is 3. Must it become greater or smaller? It must become greater, so therefore it is 10 to the power 3. So a kilometer is 1,000 meter. If you go the other way, then obviously the unit becomes bigger, then the number must become smaller, and then the factor must have a negative. Now, I don't have time now to look into that in detail, but I hope that helps you a little bit. Because, here it is, a wire length centimeter, cross-sectional area square meter. Immediately we can see there's a kilonewton, there's a millimeter. Let's take this to meter. So this will then be 3,35 meter. And meter is associated with square meter, so that's fine. Kilonewton, so take it to Newton, so it becomes 3,500 Newton. And 12 millimeter, take it to meter, will be 0,012 meter. That is your first point of departure. Make sure that you work in the same set of formula. Okay, now the first thing is State-Hooke's law. You can work through that and calculate the modulus of elasticity. Now remember, this is the calculation where you have K is equal to sigma divided by epsilon. But this one comes from F divided by A. And this one comes from change in length divided by original length. In other words, this cable, you have this cable, and the length of the cable is, there's a certain length, and now you attach the weight there, and that is the length, and now you attach the weight, now it pulls the cable. It becomes slightly thinner, but slightly longer. So this part is the change in the length, only this part here. Okay, so can you see? To calculate this, you need that, and you need that before you can calculate that. So I'm just going to show you the memo because for the sake of time, we have a problem now. All right. The weight of the object is this one, 3,500. I can probably write it in quickly. 3,500, it's Newton, and the cross-sectional area. Cross-sectional area, by the way, is if I enlarge the wire will look like this. The wire will look like that. Okay, and the cross-sectional area is that part. At the bottom, you also have that same thing. Okay, so the cross-sectional area is 5 times 10 to the power negative 5 meters square. So if you have that, you get an answer, and that answer you can bring in here. Then what about this guy? Okay, the change in length. The change in length is 12 millimeter. So if you want to substitute it as 12 millimeter, you have to substitute the original length also in millimeters. So that will then be 3350 millimeter. Or you substitute it as meter, which will then be 0.012 divided by 3.35. Either way is fine. Both of them in millimeter, both of them in centimeter, both of them in meter, doesn't matter. You can keep the centimeter and change the length to meter, etc. Doesn't matter as long as you have it correctly. So it is, let me just check if it's correct. If it's millimeter, it's 12. That one is centimeter, so it must be 3350 millimeter. If I keep the centimeter, here's another example. If I keep the centimeter, 335 centimeter, then this one must become centimeter, so then it is 1.2. And what was this one? This is the meter one. So if it is 0.012 meter, then that one, sorry, if this is 0.012 meter, then that one must become meter as well, which is 3.35. So any one of them is fine, as long as you make sure that you convert to the basic unit. Okay. And once you have the answer for epsilon and the answer for sigma, you can get the modulus of elasticity. And the last one I just want to talk about is a little bit of a calculation, or not a calculation, an argument. They say a longer wire, now let me write down the three formulae again. It's F divided by A. Epsilon is equal to the change in length, lovely part of the work, this one, and K is equal to sigma divided by epsilon. Okay. Now this type of question is very popular and only 2 marks, but 2 marks worth of achieving. Okay. You must explain something or choose something. Right. Now let's see. A longer wire. In other words, a longer wire. This part, I'm going to use this to say it's going to increase greater than. It is just for our thinking processes. With the same modulus of elasticity. In other words, this one remains the same. And the same cross-sectional area, in other words, this one remains the same, is used to suspend the same weight. In other words, this one is the same. How does this influence the extension of this wire? Now there is extension. We want to know what happens with this thing. Choose your answer from less than 12, only 12, or more than 12. Remember, they said to us that it is extended by 12 millimeter. Okay, so let's quickly see. Where do we have the most info? We want to know what that is, and we know something here. So we need to know something about this thing. This is the way a scientist argues. If I know this, then I need to know something about this and that. So let's check if I have some info for this one, because I don't have info for this one. What about this one? They tell me this and that remain the same. Now, if this and that remain the same, then this one must remain the same as well. So therefore, this one remains the same. Okay. Now, if this one is the same and that one is the same, then this one must be the same as before. Okay. So now I have a solution for that one. This one doesn't change. And I know this one becomes greater. Now the question is, what happens to this one? Now just quickly, primary school fractions. Let's say I have a value of 10. No, let's make it 100. And I put here 200 divided by 2. You agree with me? 200 divided by 2. The numerator is 200. The teller is 200. The denominator, the number, is 2. 200 divided by 2 is 100. So the equal to sign is valid. Now this remains the same, 100. This one becomes more. Let's make this 4. What must I put here so that this thing divided by 4 still gives me 100? This must become 400. So if the fraction remains the same, but the denominator increases, then the numerator must also increase. In other words, delta L increases. And this is the argument that you should have gone through to calculate or to answer this question. In other words, your answer is more than 12 millimeter. In other words, the longer wire with all those other goodies will be stretched a little bit more than the 12 millimeter. Okay, and the last one you can just check in the memo. It's a bit of theory. All right, with that, we finish the technical science question paper. Lots of overlaps with physical sciences. We see you at 2 o'clock, strictly at 2 o'clock, let's say 1 minute before 2, so that we can start with the physical sciences paper. And then the technical science learners must join us because there's a lot of stuff from which you can benefit. Bobby, thank you so far so much. See you in an hour.